to our last day. Sorry, let me say that again. Welcome everybody to the last day of this event, and thank you for all for being here. Let me remind you all that you can raise your hand, but Professor Bardarson has said that he's okay with, or that he prefers actually questions during the talk, so it's all right for you to unmute yourself and interrupt him. So we'll begin our first talk, as I said, by Professor Jens Bardarson from KTH in Stockholm. So please, Professor.
Thanks. I'll start by thanking the organizers for inviting me to this very interesting meeting, where the meeting of the mind, so to speak. So I'm a condensed matter theorist, kind of pure condensed matter, but I like working with field theorists. So I was trying to figure out how to pitch this talk really, and I decided in the end. I asked who's going to be in the audience, and it's like high energy physicists, mathematicians, PhD students. So my goal here was to kind of give the condensed matter perspective on various things that we've heard in other talks during the week. And so, like I said, I'm not a field theorist myself, but I like working with field theorists. And my favorite source of field theorists is Maria's students. So these three here, I think, are all Maria's students. And I have one more collaborator, at least Fernando de Juan. But the work that I'm going to talk about, the main heroes in that work are these three people. So Jan Behrens, my former student, who's now at Cambridge. Julia Hannukainen, who is a student with me currently still. And Jaco Ferraras, who was a postdoc here at KTH for a while, but is now back in Madrid. Okay, so we did really hear quite a lot of things during the week, kind of introductory things and very detailed things. And a lot of the things that I want to say or talk about have already been mentioned, at least, and explained in various levels of details. But coming maybe more from the angle of high energy, or field theory, maybe I should say. Well, I wanna kind of give my angle, which is more interpreting things in terms of pictures like this one here. So that will be my goal. Most of the talk, I think, will be kind of more aimed at trying to explain things to students rather than the experts. So the experts may have to wait until towards the end of the talk for something new. But I think that's okay. We've had a lot of detailed talks, so it's good to have. Plus, it's Friday afternoon here, so I feel a little bit like easy pictures. Okay, so but what is kind of the motivation of all this? Where are we meeting in some sense? And where we're meeting is really in this kind of field where quantum matter and emergence in quantum matter results in physics, which is then known either from high energy physics or in general from quantum field theory. And of course, maybe the oldest and most well-known example of that is spontaneous unit breaking and the Higgs mechanism. Let me. And this is something that happens, which is basically the same thing as superconductivity. If you take a piece of metal and you cool it down and it becomes superconducting, then you have this effect which is called the Meissner effect, that if I try to pass a magnetic field through the superconductor, the magnetic field doesn't want to do it, and instead it avoids the superconductor. And the reason for this is simply that once you are in a superconducting phase, you have a condensate, and the condensate interacts with the photons, or the electromagnetic field, in such a way that the photons get a mass. So it's precisely the same effect. And there are endless arguments which came, well, you can't really argue which came first. Superconductivity was understood first. But I think it's nice kind of to have both aspects, and there is this interplay between ideas in one and in the other. I think it's nice to meet at that point. So that's one example. That's kind of, you start from some high energy, you lower the energy, and you have some spontaneous symmetry breaking. But as pointed out, for example, by Wolovic, in mainly focusing on helium, you can also start from the many-body Schrödinger equation, and then when you low energy, you can have emergent effective theories which have enhanced symmetries. And in particular, what we are interested in this, well, we've heard a lot about this, is the case where you get quasi-particles which are relativistic. And then what you have really is that you have the vacuum. You have some vacuum which is under control, and we know what it is. Although often we are not maybe so much interested in the vacuum itself, but rather the excitation on top of that vacuum, which are these particles. Now, most of the time, when you have the many-body Schrödinger equation, you have something more looking like this. So these can be Fermi liquids, and the quasi-particles are then massive quasi-particles. But if your Fermi surface consists of points, then around these points you have a linear spectrum, and you can potentially get these kind of relativistic quasi-particles. Okay. Now this has a history, and I guess this is kind of my connection with the history. I mean, it started, or my version of the history, let's say. To some extent, it started with the discovery of graphene. Because graphene has this feature that if I fill up, so half of the orbitals are filled, so if I have these bands here, all these bands below this plane are filled with electrons, and that's what would be then the vacuum. And around these vacuum points, I have these touching points here, which are described by the 2D Dirac equation. And it's 2D, and these, I have the Pauli matrices, and the wave function is just this psi A and psi B, where this is the wave function on side A and B. Okay, and this is very nice. It has a lot of kind of relativistic physics, like Klein tunneling. There was people were interested in Klein tunneling. Then there's this whole field of gauge fields from strain that we heard a lot about in Alberto's talk. And there's this famous experiment where people found these graphene seeds and these bubbles in graphene seeds, and in these bubbles you get Landau levels. So there's that. But graphene is also interesting because this crossing point is really, the reason it's there, it's because of sublattice symmetry, mainly symmetry between these A and B points. These are just two different points in the graphene lattice. And there is a symmetry between them, and that's the reason why you have this non-crossing point. But in principle, it's easy to open up a gap in graphene. Maybe not in real graphene in experiments, but theoretically it's easy to open up a gap. And you can open up a gap in many different ways. One is just to put a potential which has different sign on the A and B sublattice, and then you just get a trivial insulator. I mean, this is just a cartoon. There's a gap, there's a filled band, and that's it. But you can also do what Haldane did a long time ago and open up a gap such that you get that these bands, like this one, has some non-zero Chern number. And what that means is that you get a topological state where you have a boundary mode, this chiral boundary mode, moving on the boundary. This is basically the quantum Hall effect. And this state breaks time versus symmetry, and as you can see from the fact that there is this chiral mode on the boundary. But then Charlie Kane was also thinking about, okay, how do I open up a gap in graphene? And he found a very interesting way of opening up a gap, where you get basically two copies of this quantum Hall effect. And you get this quantum spin Hall effect where you have these boundary modes, one moving in clockwise direction and the other in anti-clockwise direction. And I guess I took it wrong way out there. So these are kind of these 2D modes, and they're quite interesting. But we would like to, there's still the field theory of the 2D. Sorry, how do I? Here. The field theory of the 2D Dirac fermion is not quite as rich as 3D, so if we want to get more relativistic physics, we want to go to 3D. And the first step towards that was to generalize this quantum spin Hall state. So the quantum Hall state doesn't really have a three-dimensional generalization. You can make stacks of quantum Hall states, but there is a generalization of the quantum spin Hall state, which is the 3D topological insulator. And this is a very interesting state. It's also time reversal symmetric, but it only has one Dirac fermion living on the boundary. And this is quite interesting because generally there is this fermion doubling theorem that says that if you put a theory of Dirac fermions on a lattice, then you always get pairs of them. But here you get only one, and the reason you can get only one is because the bulk is in a non-trivial topological state that allows you to avoid this fermion doubling theorem. Okay, there are some subtleties to this, but that's basically what happens. So it's a form of kind of holacrophy because there is a state that only lives at the boundary. But still, it's still just a 2D, so not quite there yet. And the next step was then when people discovered the topological semimetals, where you really have a 3D version of this type of Dirac or Weyl fermion, but now in the bulk of the material. And these are interesting because they have some non-trivial momentum space topology, and of course we've heard all the quantum field theory and the anomalies and so on that people get when you study these things. And then the rest of the talk I'm going to talk about this. But so far, I just wanted to get a little bit of more broad introduction to where we got. And why is this interesting? Well, it's interesting because, I mean, I like to call this the many worlds of topological, or many worlds of quantum matter, really. The idea being that, if you want to realize a theory with, let's say, massless Weyl fermions, you can in certain materials, and then you can do various things with it, and it's interesting. And you can have, axial pseudo-gauge fields, you can have torsion and all these things that you can play with. And sometimes you can do this with things which you don't really realize in the real world or in the standard model, at least not so far. So if you don't like today's world, I mean, with pandemic and climate change of all that, you just can pick your favorite world by picking your favorite quantum matter and then study the physics within there. So, I mean, there are further extensions of these. If you take superconductors, you can get Majorana fermions which are their own antiparticles. Fractional quantum Hall states have non-abelian anyons. Recently, we have realized things like fractons and so on, which are particles with some non-trivial symmetries and so on. So there is a lot of fun things to do in here in this, to realize in these worlds, the many worlds. So not the many world interpretation, but the many different worlds of quantum physics. Okay, so we've seen this before, the Dirac equation. Now, if I try to think about what this corresponds to kind of in the condensed matter, well, this particular here, when I have a mass, it corresponds to 4 bands. It looks like I only have 2 bands, but there are actually 4 bands because each of these is twofold degenerate because of Kramer's degeneracy. Namely, there's a time reversal symmetry and inversion symmetry that forces me to have degeneracies of all bands here. Now, if the mass goes to 0, then let's see. I can see in the chat, R stood for relativistic quantum field theory. Okay, if I put m equal to 0, then the Dirac fermion decouples into 2 Weyl fermions, and these Weyl fermions are right and left-handed. And I've plotted them here with these arrows, and I'll explain in a second what that means. And in this particular choice of basis, there is this 5th gamma matrix which takes values 1 and -1 in the for the 2 fermions, and this is basically the chirality of the fermions. When I've written it like this, there's still a degeneracy because these 2 bands are sitting on top of each other, And this is what we would call a Dirac semi-metal. When we have the right and left fermion sitting on top of each other, there's a degeneracy. And you might ask, why doesn't I open up a gap? Well, generally you would open up a gap unless there's some symmetry that kind of protects one from interacting with the other, forcing this off-diagonal element to be zero. But we'll come to it later. I wanna discuss a little bit how to get these not to be degenerate. But first, let me just talk about this theory a little bit more for one of these. Namely, if I have a Weyl semi-metal and I can somehow separate these in momentum space so that they're not sitting on top of each other, and if I look at one of them will be described by this theory P dot sigma, which is exactly the same theory that I wrote down for graphene. But there's a difference, and the difference is that this is in 3D, and because it's in 3D, I need to use up all the 3 Pauli matrices. And once I have used up all the 3 Pauli matrices, that means that there's nothing I can add to this that will open up a gap. So open up a gap here is hard, while in graphene it was easy. And the reason it's hard is actually because this crossing point is a monopole, and it's a monopole of Berry phase or Berry curvature. So if I take the wave function up around this point and I calculate the Berry phase of it, defined like so, then it turns out that if I integrate the Berry curvature around this point, it's an integer, and it's a Chern number basically. Now, if I think about Dirac monopoles, then the reason that this thing is non-zero is basically because there is a singularity. There's no way to kind of write one gauge where I capture the full wave function everywhere, or I don't have one set of coordinates, so to speak. And that's basically reflected in the fact that there is a Dirac string coming out of this monopole, which is this singularity here, where if I take the wave function here and if I move it around, it will pick up a minus sign because I would rotate the spinor by 2 pi. And okay, I don't know what happened there. Sorry, I'm trying to get used to my iPad here as a controller. Okay, and there is this Dirac string that goes out of the monopole and it goes to infinity in principle. At least if I have a monopole in electromagnetism. But now these monopoles are living in the Brillouin zone of the lattice that I'm sitting in. And therefore it cannot go to infinity because there is no infinity. The Brillouin zone is a torus, so it's a compact manifold. And in fact it has to end up in a second monopole with opposite chirality. So these monopoles always come in pairs. This is just the fermion doubling theorem. Okay, so what does this mean? Well, it means something quite interesting in terms of condensed matter. Namely, I have these two Weyl points, but if I zoom out in energy, of course they are just a low energy theory or low energy part of the bigger band structure. But if I now go and I fix let's say I fix the momentum value, so this is the kc direction here, so I fix the kc to be some value here in between the two Weyl points, then the two-dimensional band structure that I have in this plane here is gapped, and it turns out to have a Chern number. But as I discussed in the case of graphene, the Haldane state was just a band with a Chern number. So this is basically a quantum anomalous Hall effect. While outside of here, the Chern number is 0. But that means that if I make a finite sample, then the Chern band will have this boundary mode that I showed for the Haldane Chern insulator or quantum anomalous Hall effect. So there's a boundary mode, and this boundary mode is sometimes referred to as a Fermi arc, and that state is just between these two Weyl points. Okay, so actually the full theory that I have is these two Weyl points, and then in between these two Weyl points there is this Fermi arc state. Okay, So, but in order to get these 2 points separated in momentum space, I really necessarily need to break either time reversal or inversion symmetry. And the reason for that is the following. So inversion symmetry inverses momentum. It also inverses position, and therefore it leaves angular momenta invariant. That means that it relates, if I have an inversion symmetric system, it relates the energy of the spin up at k to the energy of spin up at minus k, and the same thing for spin down. Time reversal symmetry, on the other hand, doesn't change position, therefore it flips both momentum and spin, so it relates the energy of the spin down state, say, to the energy of spin up state at minus k. Of course, if I have both of them together, then the energy of spin up at k is equal to the energy of spin up at minus k, which is equal to the energy of spin down at k. So all state are doubly degenerate. But now, if I don't have both of them, if I have one of them, let's say I have an inversion symmetric system. So I break time reversal symmetry, and I have one of these Weyl points somewhere away from a high symmetry point, or the center of the Berlin zone, because otherwise I would just map the point to itself. If k is equal to 0, then I necessarily have to have another point somewhere, and the inversion symmetry actually maps a point with, let's say, right-handed chirality to a point with left-handed chirality, basically because as I do the inversion, this state goes to that state with the same spin, and then I follow the rotation of the spin around the point, and I see that this is right-handed, this is left-handed. While if I have time reversal symmetry, then the time reversal symmetry will map right-handed fermion into a right-handed fermion, because now I flip the spin, and therefore I get the same rotation around the 2 points. But I needed to have even number of right and left-handed fermions in my system, and therefore somewhere else I will have left-handed fermions. So if I have time reversal symmetric system, I need to have minimum 4 points. So I have at least 4 Weyl points if I have time reversal symmetry, but I can have only 2 points if I have inversion symmetry. Okay, so where can I expect to find such Weyl points? Well, if I just imagine taking 2 bands and I want them to cross, that is what I would say as a Weyl point. I just write down the 2-band theory, I limit myself to these 2 bands, and then I expand around the point. Well, what I see is that I just need to satisfy this condition that the value of b at the crossing point is 0. And these are 3 conditions, because it's a 3 vector here, because there are 3 Pauli matrices. And if I'm in 3 dimensions, then I have 3 momentum that I can tune, and therefore having these crossings in 3 dimensions is very generic. So basically, whatever band structure that I take in 3 dimensions, I will have bunches of these Weyl points, these crossing in it. Okay, so why was it only in 2014 that people discovered it? Well, and then here's just I can now rescale these things so that I get the k dot sigma term here. Well, the reason that it took a while to figure out is because you need these Weyl points to be close to the Fermi level, because otherwise, who cares? If they are somewhere deep down in the band, they're basically part of the vacuum, so to speak, and they're never excited, and you don't care. But there are several materials now. This is probably an old slide. I should update it. There are even more materials now, especially with the magnetic Weyls. So you can easily get materials which have these structures. Okay, so I want to focus on kind of this structure now. Okay. Now we saw this. I can go a little bit quicker here because we saw this before.
Professor Bardarson, I think.
Oh, there are questions. Maria,
yeah,
sorry.
There's a question.
Yeah.
So please
go ahead.
Yourself, Professor Malar.
Hi, sorry, I raised my hand, but I think you didn't see it. So it has to do with 1 or 2 slides back. No, the following one.
The one after this one.
I think so, yeah.
This one.
Yeah, yes, this one. So you explained that the emergence of a Weyl node relies only on the availability of more parameters than equations to satisfy, and that's a feature of 3 dimensions. Is that right?
Well, equal number of, so I need, in order to have that, I have a crossing in the eigenvalues of this 2 by 2 matrix, I need that the vector multiplying the sigma matrix goes to 0.
Yes.
That's so when I get a degeneracy. So that's 3 numbers. So these are 3 equations with 3 variables.
And then you, because you have some coupling in your Hamiltonian, you have a 4th parameter, which is the Hamiltonian parameter, and you can tune this parameter so that these 3 equations are simultaneously satisfied. Is that right?
That's right. It's just the momentum. In the momentum, there's somewhere in momentum space, this will be generally satisfied.
Yeah.
There will generally be a solution to this.
So any 3D material, therefore, would have a solution.
Yeah.
So my question is, what's special about Weyl semimetals?
Yeah. So that was. Yeah. Finish the question.
Yeah. That because since these equations can be generically satisfied just because you are in 3 dimensions, what's the role of symmetries? I mean, these 3 equations, they do not rely on the presence of any symmetries, because you just have 3 equations and you have enough number of parameters which you can tune to satisfy the equation. So what's the role of symmetries? Why are they important at all in Weyl semimetals? That's the question. Thank you.
Well, so they are, in principle, they are not important. In practice, they are important in order to simplify the search for materials where these Weyl points are close to the Fermi energy.
I guess it has to do with what you were going to say next, probably.
Yeah, exactly. So that's the, if I just take any band structure, you look at it, you will see these points, but they are somewhere deep where you don't care about them. So yeah, but I mean, you don't need any symmetry to have a Weyl semi-metal.
Yes, that's my question. But then eventually, when you talk about Weyl semi-metals, people always talk about the symmetries. So that's something that I always ask myself, why are they important? Because in 3D, you can always find the solution to the gap closing equation.
Yeah, and that's just because you want to be close to the Fermi energy. But the symmetries are of course important then once you want to look at the details. I mean, for example, in tantal marcionite, that has a bunch of these mirror symmetries. So that's inversion breaking, and remember I said you need to have 4 Weyl nodes in the inversion breaking case. So I get 4, but then because I have these mirror planes, they start to multiply, because once I have 4, I need to have the mirror image of those 4, and so on and so on. So that's why in tantal marcionite I have quite a lot. 12 or 16 or whatever it is.
So could I maybe understand that the symmetries are a consequence rather than the cause of the Weyl nodes?
No, the symmetries are not a consequence of the Weyl nodes. They are additional structure on top of having Weyl nodes. And then, of course, if you want to have, for example, here, that's a magnetic Weyl semimetal which has an inversion symmetry. If I want to have the Weyl nodes, if I have 2 Weyl nodes, let's say, and I want to have them at the same energy, I need to have an inversion symmetry or some symmetry that enforces them to be at the same point. But generically, I would get something. Okay, this is a really bad. So generically, I would get something like this, where I have 2 Weyl nodes, but they are not at the same energy, and here I have no symmetries. But so the symmetries then play a role in kind of aligning the energies of these Weyl nodes.
Okay. Thank you.
Sure. thank you. Okay, so but if I have, I have this field theory here, and when I have a mass, there's a U1 symmetry, but once I have the Weyl point, there's an additional U1 symmetry, which is just having the opposite sign for the two left and right-handed fermions. And if I write out the conservation law that come from these symmetries, then I get, this U1 symmetry to say that the total charge is conserved, while this one says that the axial charge, namely the difference in left and right-handed fermions density is conserved, which means that they're independently served, both of them. The charge of the right and the left-handed fermion. But if I now take a field theory of one of these, or a Hamiltonian of one of these, and I put it in a magnetic field, I very quickly see that actually it's anomalous. It doesn't conserve the charge. And the easiest way to see this is to go to kind of the Landau level picture that we heard about in a couple of talks, but let me explain what that is. So basically, I want to solve this Hamiltonian by going into Landau levels. So I introduce these creation operators, which are just this linear combination of x and p, but shifted with respect to one of the momenta here. And once I do that, I get Landau levels. But Landau levels that are dispersing in the third momentum direction, because I didn't use the third momentum here in these Landau level operators. So I get these dispersing Landau levels. But that's if n is different from 0. If n is equal to 0, I get the 0th Landau level, which is just linear, and it's chiral, like this. And of course, all of these Landau levels are degenerate because the energy doesn't depend on P2. If I imagine P2 being pointing into the picture, then all these levels, Landau levels, are coming kind of out of here. And all of them have a degeneracy which is given by this Landau level degeneracy. Now I fill all of these levels here, and then I apply an electric field in the direction of the magnetic field. And if I do that, then I see that the change in the momentum just goes proportional to the force, which is E times E. And I see that the density of particles here is changing. And how is it changing? Well, it's changing according to, I just count how many states have crossed the original point here, and it's proportional to the force times the degeneracy of the bands, and that just gives me E dot B. So the number of left and right-handed fermions is changing proportional to E dot B. And there's a chi here, which is plus or minus for the two, for the left and right-handed fermions. Okay, so already one Hamiltonian of one chiral fermion doesn't conserve charge, so there seems to be a problem. But of course, there isn't a problem. We understand what's going on. I mean, what is going here is that the field theory is actually anomalous. It just means that the classical symmetry is broken by quantum fluctuations, and this was discussed in all detail in earlier talks. So I'm not going to repeat that. But at the level of the kind of condensed matter picture, you look at this and you immediately say, well, this cannot be the full picture because this band structure lives in the Brillouin zone. The Brillouin zone is a torus, and if I have a continuous function on a torus, it cannot cross this axis only once, because that's not a periodic function. So I immediately see this is not an allowed band structure. And the reason, of course, is that there is always a second Weyl node with the opposite chirality, and the 0 Landau level there disperses in the opposite direction. And then they're connected somewhere deep in the vacuum or in the high energy in the bands. Okay. So now I see that when I have the if I fill this band up here, I apply an electric field, I'm just shifting left-handed fermions to right-handed fermions, like so. Okay, but there will always be some disorder, and disorder, what does disorder do? Well, it will scatter particles with a given momentum into particles with some other momentum. And in particular, if I have, you know, disorder which is fine, varies on a very small scale, in fact at the scale of the lattice spacing, it can scatter this fermion into that fermion, and with some scattering time tau v, and you get this relation that, you know, you have this pumping from the electromagnetic field that is pumping left-handed fermions into right-handed, or vice versa, but there's always some disorder that will counteract it, and eventually this term will dominate and you get a steady state, non-equilibrium steady state, where there is a difference in the chiral potential between the left and right-handed fermions. Okay. Now, once you have this mu5, you have this chiral magnetic potential. If you apply a magnetic field, you will get a current proportional to the magnetic field. So it's called the chiral magnetic effect. And it's just because if I have more right-handed fermions than left-handed fermions, I get a current. Essentially what it is. Okay, and this is supposed to lead to a negative magnetoresistance in materials, which was one early experiments claimed to see the anomaly through negative magnetoresistance. Now it turns out that you can get a lot of other reasons that can give you negative magnetoresistance, so it's not quite that simple, but still it's quite encouraging. Okay, so I've basically discussed this field theory now from the perspective of condensed matter. There is the Weyl nodes, and there are two of them. I have some external electric field, and then there is this separation here between the two Weyl nodes, which is this vector b mu, which just tells me what the separation between the two nodes are. But if this kind of looks like it's a chiral Gates field entering in here, so I could imagine that if I allow the Weyl node separation to vary smoothly in space and time, that I can just take this field theory and I can replace this A5 with a function A5 that depends on position. And I think this we saw this was all the details of how this works were given in Alberto's talk yesterday. But once I have that, I have this function B here, which depends on position and time. That means that I have this axial magnetic field and axial electric field, which are just the curl and gradient of B and B0. So I have these B5 and E5 that can interact with my material. So now I can wonder where can I get a situation where I have non-zero B5. Okay, Alberto discussed how you get this from elasticity, but there's one example where you always have it, which is at the boundary of a material. So if I take a Weyl semimetal, well, it has a separation. It's at the boundary. It's interfaced with vacuum. Vacuum doesn't have any separation. So the separation vector goes from some constant value in the bulk to 0 in vacuum. And as it does that, it generates a B5 localized at the boundary of the surface. And this B5 then has Landau levels, and in fact the Fermi arc is just the 0th Landau level of this B5 localized at the boundary of the Weyl semimetal. Okay, so so how does this Fermi arc enter into this picture here? I mean, there doesn't seem to be any Fermi arc in this picture that I draw of the two Weyl cones. Well, I have to remember that what I said is that these are degenerate in the ky direction. So if the ky direction is in here, so if I pick some energy and I look what this looks like into the plane, this is what I have. It's just a line, and this thing is just a line here. But these lines are Landau levels, and these Landau levels have this position momentum locking, which was that when I wrote down the creation operator of the Landau levels, I had to shift the position by the momentum in the y direction. Okay. So if I vary along this line, then I'm changing ky, which also means that I'm changing the position, and therefore this cannot go on forever, because at some point I will hit the boundary, and on this side I will hit one boundary, and on the other side I will hit the other boundary, and there I will hit the Fermi arcs, which are the surface states, and the surface states actually connect the left-handed and the right-handed bulk states. And the length of this thing is then proportional to b. Okay, but imagine I had B5 that was uniform in the bulk. Well, B5 is a magnetic field which has the opposite sign for the two left and right-handed fermions, and therefore their zeroth Landau level will disperse in the same direction. So if I use the same argument as I did for the Chiral anomaly here, it would seem that if I apply an electric field, I'm generating charge, and it's not cancelled between the two. So it looks like the actual charge, not the axial charge, but the actual charge is not conserved. This is what's known as the covariant anomaly. It looks like the charge current is not conserved. So there's a nice way to understand this in terms of these pictures of these Fermi arcs and the connected by Landau levels. Namely, I said I had this is the same square I had before, and the size of that square is proportional to b. So if I now plot the energy as a function of kx and kc, it's just this inverted kind of, I don't know what that shape is, some kind of cone. But if I now have some non-zero b5, well, it will change the length of these Landau levels with opposite signs. So it will shorten one of them and it will lengthen one of them. And that will kind of morph or change the shape of this one a little bit, but it's more or less the same until, of course, the point where b5 becomes equal to b, in which case I get a twist of this structure here. So I get a twist between the Landau levels and the Fermi arcs. So I call this the bow tie. And then I have these bulk states here, but now the Fermi arcs have this kind of curvature here. And if you look at the spectrum now, then I had these P5 induced Fermi levels, but there are also these Fermi arc states that are dispersing in the opposite direction, and I have this nice bow tie spectrum. And once I take into account the contribution of these Fermi arcs, then charge is conserved as it should be in a condensed matter system. And at the field theory level, you go from here to here by adding some Bardeen polynomials to the charge or the current. But that's how it works in the So I'll use this one from now on. So this is what I've discussed so far. I've discussed how you can have these axial fields and axial gates fields. And this leads to this anomaly equation. Okay, as I promised, there will be towards the end maybe something new for the experts. So now I'm gonna discuss something a little bit more new, namely how to realize these P5s and E5s in different ways than strain or at the boundaries of Weyl semimetals. And this is work that I did with my student Julia Hannukainen and Iago Ferraris and Alberto Cordillo. Okay, so the idea here is that if I have a magnetic semimetal, then the Weyl node separation is induced by the magnetization usually, because it's a magnetization that breaks the time reversal, and that's the time reversal breaking is what leads to the separation of the two nodes. So then this vector B is actually just proportional in the simplest case to the magnetization. And now any magnetic material usually has some domain walls in it. It's not one domain where all the spin point in one direction. They only point in one direction in some domain, and then at the boundary between two domains you have this variation of the magnetization from pointing in one direction to pointing in the opposite direction. But now I have a variation in the magnetization, which, since it couples to the Weyl node separation, is a variation in space of the Weyl node separation. So naturally I have a B5 localized to the domain wall. And if I calculate the B5, this is how it looks like as a function of the position along the domain wall. I have some non-zero value. It's its maximum precisely in the middle of the domain wall, and that's it. But what about E5? Well, E5 is I need some time dependence of this domain wall. So how do I get time dependence of a domain wall? Well, basically I need to find some way of moving the domain wall, and the simplest way of doing that is by applying a magnetic field. So if I apply an external magnetic field, let's say in the z direction, then these magnetic moments want to align with that magnetic field. So they start to rise up, let's say. And at the same time, these start to rotate around. But effectively what that means is that I'm transferring spin up, or I'm taking one of these magnetizations down to become spin up, is effectively meaning that I'm moving the domain wall. So once I add a magnetic field, the domain wall starts to move. And you can write down some effective field theory that describes this, and you can use these collective coordinates, which is just the center of the domain wall and this angle of this center spin here phi, and then you get these set of equations here that describe the dynamics of the domain wall. So x is then the velocity, it's proportional to b, but there is also this rotation of the domain wall. But if b is small enough, less than some critical value given by this ratio of the Gilbert damping constant and some other factors, not that important, there's some critical value below which phi dot is 0 and domain wall just moves as a rigid thing. While if you go to b, which is larger than this critical value, then the phi dot is no longer 0, but the domain wall is moving, but it's also rotating. Now this is important. This is called the Walker breakdown, but it's important because it turns out that the E5, which was, as you remember, it was just E5 was whatever it was, dt times b. E5, if I'm in this regime where phi dot is equal to 0, E5, there is a non-zero E5, but it's orthogonal to B5, so that doesn't activate the axial anomaly. While once phi dot starts to rotate, I get a non-zero E5 times B5. And once I have that, well then the domain wall is moving, but because of the axial anomaly, I have a non-zero E5 B5, which means that I'm generating an N5 or an axial charge localized and moving with the domain wall. And this is the actual calculation. It's the mu5 at the center of the domain wall as a function of time, and it oscillates. And this is as a function of position. So at time t1, it's let's say it's positive and maximum at this point. This is a second curve at t2 where it's has the opposite sign here. And how would I go about detecting this? Well, one way is to use the chiral magnetic effect. So there will be, once I have this mu5, there will be a current proportional to a magnetic field, and there is a magnetic field already that I'm using to move the domain wall. And as I have a charge current and circulating charge current at the domain wall, this will lead to radiation. And we've calculated the radiation. Details are not so important. I mean, it was a lot of work, so I don't want to but the details, the exact numbers are what they are. The upshot is really that you don't need such a large magnetic field for the amount of radiation coming out to be detectable. That's kind of the opposite of this thing. Okay, you can also use, this is a different work, you can also use the anomaly to do spintronics. I don't have time to go into details here. This is the equation of motion for the magnetic, for the magnetization in one of these domain walls. And in this work, we show that there's an additional torque term here, which is induced by the anomaly again. So you can have a torque induced by the anomaly, and the interesting thing is that you can use that torque to actually flip the orientation of the domain wall. So you can use an electric field to flip a domain wall that has an angle pi over 2 into a domain wall with an angle minus pi over 2. So that's quite nice. So you can use an electric field to tune domain walls. Okay, I think I'm reaching the end of my time here. So there is additional things that I actually have, but I knew I wouldn't have time. But I'm going to flip through it just to advertise. Namely, that's this thing that we heard about that now I've basically discussed the axial fields, but if you look at the, you can have variations in tilt, for example. I always had my nodes being upright like this, but if you have a tilt and you can put position dependence on that tilt, and that will induce variation in these frame fields in the Hamiltonian. And these frame fields can give you either some curvature, although these are higher order, or torsion. And we heard about torsion in several talks. We looked at something interesting, which is axial torsion. Namely, can I have, just as I had an axial Gates field, can I have an axial torsion? And it turns out that you can if you have some tilted interface between a tilted Weyl semimetal and non-tilted one. Okay, we did some calculation to show that this would lead to some currents that you could maybe see, although we used the anomaly, and as we learned from Chiral Landau in Jako's talk, the anomaly for the torsion is not so, it can be taken away. Okay, so that's what I wanted to say. There is a lot of interesting physics here that kind of brings together many different fields. A domain wall motion in magnetic Weyl semimetal. Who would have thought that actually corresponds to axial fields and axial anomalies? And there's this interplay between spintronics, topological states, quantum field theories, and so on. And then you can do various things, like you can vary these tilts. You can get torsion, you can get curvature, and so on. So I think this is very, very exciting field to be in. Okay, I'll take some questions if I still have time. Thank you for your attention.
Okay, thank you, Professor Bardarson. So we have time for some questions. Are there any questions? Oh, okay. So, Professor Urrutia, please go ahead.
Yeah, I just want to ask, when you calculate the radiation in this domain wall, do you have a modified electrodynamics? Or, because you have the domain wall there, you have to fulfill some boundary conditions, or it's just a standard electrodynamics, or you have some modification?
We just did a very standard calculation where there is some current, and then that current generates radiation in the usual way. There are additional terms. For example, you have magnetization, which is rotating, and that also generates currents that you have to separate between. So that there are, but we just wanted the very kind of simplest estimates of whether this effect was potentially detectable or not, and our conclusion was that it is potentially detectable. But I think if you actually want to do the experiment, then probably one would want to take into account all the details that we skipped.
Okay.
But for the physics, we didn't think that was so essential at this point.
Okay. Thank you very much.
May I have a question? Regarding the torsion, did I miss that part, or you were not speaking about torsion? I kind of...
No, I kind of went through it very quickly. So
okay, that's why that part. But it was related to defects, or?
yes, well, so yeah, I mean, torsion generally is due to some defects, as I think Jaakko talked about this to some extent. But what we were discussing is this axial torsion. So we were looking at the equation for the anomaly. I mean, we learned, we heard, I should say, rather than learned. We heard this week that okay, the anomaly due to torsion has some problems. I mean, basically the coefficient is cutoff dependent, so it and you can kind of get away from it. But but let's not worry so much about the anomaly part. But just as you can have these torsion fields, what we asked is, oh, could I have a axial torsion? So torsion that is has opposite side for the left and right-handed fermions. And for that you need to have well, basically you need to have this situation where the left and right-handed fermions are tilted in opposite direction, but then there's a defect which is the interface between the, so it's a heterostructure between non-tilted and tilted. That was kind of the simplest way that we thought about being able to get this. And then you get this axial torsion, but only the time component of it. I don't know how to get anything beyond that at the moment.
Thank you.
I mean, I know how to get the E5 by then adding phonons on top of this, but the time component of E5, but other than that, I don't know. I think this is quite nice, actually. I don't know what to do with it, but I think it's just as a curiosity, it's kind of nice.
Yeah, sure. Thank you.
Mariana.
Okay. Professor Mogat?
All right. No, actually, my question has been just answered. It was about torsion.
Okay.
Thank you. Actually, if I may, I would have a simpler, more practical question, which is not directly related to your talk, but it's just a curiosity. So we know that Weyl semimetals are accidental semimetals, right? So in practice, how robust are these materials? Because since you need to tune parameters of the system in real life, so does it require fine tuning, or the Weyl semimetallic phase survive within a reasonably large parameter regime?
Well, I would say that no, it doesn't need any fine tuning. What is maybe hard in the material science sense is to get materials where the only thing at low energy are these, let's say, these nodes. So in many of these materials, you will have various trivial electron or hole pockets in addition to the Weyl nodes, and also having the Fermi energy close enough to the Weyl point that the dominant terms are the anomalies is also maybe not so hard, but to not so easy. But to have, I mean, once you have these Weyl points close enough to the Fermi energy, this is quite stable. I mean, there's no, because it's, I mean, they're topologically protected. You really need strong disorder or some very, very structured disorder that you generally don't have. But then when you want to do the experiment, you have to separate the signal from all the other stuff that's around. That is hard, but that's an experimental problem, I think, mostly.
Okay, thank you.
And with that, let's thank Professor Bardarson again.
Thank you.
And we'll now move on to the next talk. So, Professor